So we are all together for our wide bandgap session, mainly on capacitors. We had already very successful the last 2 days, the active switches, the new devices in GAN and SiC challenge also the passives, and we had the previous session about magnetics. So now we are about capacitors. I need to ask my backstage. They are shaking their head. There is no question from outside so far. So we have to get it a little bit between us, stimulated what are the challenges for capacitors in the new systems that uses wide bandgap devices. If it's SiC or if it's GAN, does not matter. It would be nice to hear your understanding what you see in these challenge times. Hey, Ron, welcome. We see your picture.
Yes, thank you. Sorry, I'm embarrassed. I had this screen. I was adjusting all of the adjustments, right, and it was the screen shutter that was closed. Oh, I'm embarrassed, but I'll admit it.
Ron, I remember that people run around with the photo camera and had a cover on the lens and were wondering when they developed the film a long time ago that all the pictures did not show anything they had pictured. So
I think I'm one of those.
and I remember that was in 1978. I was a tent and the car and a friend driving around Norway. And on one of, you need to take a lot of ferries to get across the fjords. And we were standing early in the morning on one of the ferry and not too many cars there. And two old ladies, and there were these compact camera, and the one lady had the compact camera and hold it like this. And I was thinking, hey, can I go and tell her that she fully covers the lenses? She just looked through the viewfinder. And I went to her. It was German lady, so it was easy to talk to her. I said, hey, lady, if you want to get good pictures, be careful. That's the lens where the film gets the exposure, what you are picturing. And I showed it to her, and she said, thank you so much. I was wondering that only a few pictures from every trip I made were good to be enlarged and printed out.
Yeah.
So these are the stories when I was a young man. Now we're back to capacitors. Ron, you do mostly KYOCERA ceramics. That's what I have in mind with AVX KYOCERA.
Well, that's true. The company started with ceramics, but there's quite significant work going on in tantalums or tantalum polymers, and also films, and to some extent electrolytics as well. So there's more material systems which are occurring and different packaging methods.
Okay. So are there special plans to serve the market for the applications where SiC and GaN is dominating the future?
Yes, basically, there's a couple of things going on within the world of ceramics. The intent is to have higher temperature devices as well as higher voltage devices. There's a general effort now also to improve the DC bias characteristics of the device, and that's occurring through ceramic formulation advances. And then also from a film capacitor point of view, well, there's always the physical aspect of things where we try to develop or configure the pucks or the bobbins in lower inductance configurations, smaller configurations. But there's also integration of NTC sensors and some other things. That it's more of a physical development, configuration development in the world of films. Yes.
Thank you, Ron. Any comment from Thomas?
Yes, maybe
okay.
I will just briefly talk about our work here at the university. So I also think that with some research in material science, we can improve also, let's say, electrolytic capacitors and also film capacitors, which is my major work also for the use of in the wide bandgap applications. We work right now on high voltage polymer solutions for aluminum electrolytic capacitors. Right now, we established already breakdown voltages up to nearly 600 volts, and we are going towards even higher voltages right now. And this is quite new that you can use polymer electrolytes for high voltage applications. And second, we work on new dielectrics for film capacitors to extend the temperature stability, because when you bring film capacitors close to high temperature and high frequency switching devices, there might be some deterioration, and we work on that as well. So this is mainly material science, and we have published recently several papers in that field, and you can check them out if you Google us. So Thomas Ebel and CIE, you'll find a lot of papers about that work. That would be my comment here from the university side.
Thomas, thank you. And now I like to hear what Rob may contribute to our.
Hi, everybody.
Hi, Rob.
Hi, Bodo. So I'm replacing Mike Wens here. He's also listening, but he cannot comment at this moment because he's on the road. He gave a nice presentation about our capacitor measurement system called MinDCet, where he explained the principle and the advantages it has for exciting capacitors with hard switching voltage and current, which is ideal to characterize capacitors and also to do development and research on it. So I think it perfectly fits into what you are all working on. And I was told that I can be here to answer any questions you might have about the machine. So I'll be glad to help you out on that.
I think your colleagues on the stage may have questions to you on that subject. Maybe Artin has something to address to you. We try to stimulate our auditorium, but sometimes they are quiet, just listening, and hesitate to put questions out. I have seen that in real conferences. So normally what I did sometimes I had put some questions out from my side, but I think it's so specific what you're doing that I do not want to put general simple questions out.
Yeah.
It's better to get you together talking about what you can do and improve and what you are looking forward to. So
maybe if I may comment on that, Mike
Yeah.
also gave a very good presentation. I also saw it myself again, and it covered very well the principle and examples of what you can do with it. And of course, I can give you some more insight into it. I think the most important thing to understand from our measurement machine is that we don't do any simulation and we don't use sine waves. We actually use square waves, so square wave current, just like in the application. And these square wave currents, they are applied to your capacitor, the capacitor under test, or CUT, as Mike likes to call it. And this is being measured, and these measurements are then processed in software to calculate the AC power loss. And this is something that has never done before. So that's why we invented it. And we got this idea from our other measurement device for inductors, which does more or less the same thing, but for inductors. And so we made this machine as it can serve very well for capacitor manufacturers and research institutes or universities who also work on this topic. And the machine is optimized to be easy to work with. So it might look very big and difficult, but it's all software controlled. So you just put in your frequency, duty cycle, current and voltage, and then it runs for you. So of course you need to put in your capacitor, and then all the rest is automated. So within 30 seconds you get a result for one switching condition. And the options are legio, because you can go to very high current, 24 amps peak to peak. So even big capacitors can be excited to high currents where you can heat them significantly. And this is very valuable information if you want to compare capacitors in an application where power loss matters a lot, because you want to improve efficiency. So that's one of the things.
Rob, thank
Yes.
you. I would ask Thomas, as I know Thomas is coming from a manufacturing background historically. That could be something very valuable in your area, Thomas. And maybe you have some comments to it.
Yes, I think it's interesting. The thing is that 24 amps, you say it's a big current, but when we talk about usually the link caps for automotive use, for example, it's a recent current. So we talk about much higher currents here.
Yeah.
And the thing is, then of course we talk here about DC with a ripple current on top. When we talk about AC applications, and I'm not, to be honest, not so familiar with your device, but it's anyhow interesting because testing is always, especially AC testing, is very often difficult. And when you have filter caps, for example, then there it's a stressful environment with an AC. And if you can help the developers to get improved mission profile testing with AC, this is of course a big help. And I think it's so. I will look into more detail into your device. It sounds interesting. But just my comment would be 24 amps is okay, and maybe you know that.
Well, I've while we were developing the machine, I've tested it with a lot of capacitors, and these capacitors go from small ceramics 0603 to very big electrolyte capacitors. Of course, there's another range when you go to automotive power drives or even higher power, like in trains and so on and so forth. Then 24 is maybe a small current. But for what I've seen, for the regular capacitors used in DC-DC converters, 24 amps is a lot. And another comment on this. So what I've or what we have seen is that often it's also underestimated what power loss you can generate even with a limited current, because if you have a high voltage ripple, you can make the part heat up even at the lower current, because in the end it's voltage times current that holds the power and the power loss.
No, absolutely correct. So
yeah.
This is no doubt. This was just only a comment which came to my mind, because usually we are right now testing higher ripples. Anyhow, when we talk about small caps, then this is of course already a nice possibility. But I really will look more in detail into your device. Yeah. Interesting. Thanks a lot.
And please feel free to contact me. What we always do, because this machine is so specific, it's so niche, is we offer free sample measurements for your part, so you can really get an idea how it can be beneficial for your research or the development of your parts. So yeah, that's how we always work. Thanks for your question.
Thank you. Any comments from Artin or Ron?
Yes, I have a follow-up question for Rob, if you don't mind.
Of course.
I wonder if so you use your machine to measure the capacitance itself and the parasitics, perhaps the ESR and ESL. I wonder if you have compared the ESR and ESL that your machine measures, not the machine specifically, but the method that you're using to measure those parameters by applying a square wave or a pulse rather than a sinusoid. two measurements that are based on sinusoidal excitations, like VNA or other methods. I just wanted to if those parameters, mainly the parasitics, the ESR and ESL, change significantly under using these two methods.
So yes, we did some limited comparison between existing values from datasheets and what we measured. And often what we see is that it matches pretty good. What we also did to verify our system is did some very simple testing where we added resistors in series with the capacitor and then see if the value changed accordingly, just as a verification, and that fitted very well. So this gives us very good confidence about this measured as well, this measurement method. So yeah, does this answer your question?
Yes, it does. So then I'm thinking. So since the outcome of this method is closely matches the other methods, so what would be the main advantage of using this method rather than the other ones? Because the final outcome is similar, isn't it?
Well, like I said, we only tested a selected, or compared the selected number of components. So it might be very well that it is different for some components, especially here we can measure at high frequency and high current. So there we cannot really compare ESR. Also when the part heats up and so on and so forth. So measuring at real life conditions is always better than doing it the classic method with a small sinusoid. There you're also limited. So
sure, understood. Thank you.
Thank you. You're welcome.
Rob, I just had a quick comment and one question, please. You know, I think it's a great idea, and as Thomas had said, you know, of course, the high value, high current applications are out there, but many times there's such a volume in, you know, the switchers, and where we're worried about the high efficiency of some pretty high volume devices. So intermediate and small parts would have a real interest, and there's quite a difference between the way we'll test on a production basis versus R&D and characterization on lots. But is there anything you could talk about regarding the minimum ESL resolution you might be able to find? We're trying to drop ESL dramatically. Of course, it's difficult based upon how we connect to things, and we have to do a lot of de-embedding of circuitry. But any comments about how what your minimum types of ESLs might be measured?
Mm-hmm. Yeah, so indeed, the smaller the ESL, the harder it is to measure. That's in general something that's a fact. So what I've measured is ESL in the range of nanohenries. So let's say tens of nanohenries, up to an accuracy to plus minus 1 nanohenry. That's what I would say. And even that's an important thing to understand. Even if the value is not as accurate as you want it to be, it's easy to use a machine, or it's still a big benefit if you want to compare parts. Huh? If you have another part which should be an improvement, if the ESL doesn't go down, then you know, even if the absolute number is not known this correct, it shows a change.
Yeah, that's very true. That's, in a way, we're actually at the point now where we're looking at relative improvements, because as you say, it's so difficult to get that that low ESL number. it's surprising to see where ESLs are going. It's important that they reduce, but it's almost surprising we're getting as low as we are for the caps that we're building, right?
Yeah. And, yeah, at a certain moment, the track on your PCB will have much more ESL than the capacitor itself. So
Exactly.
Yeah, that's right.
it's a good point, indeed.
And I have a question also, Rob. I saw I was on your website and you specified it right now up to 70 volt, right? Your device.
Yeah, input voltage.
Input voltage.
Yeah, so the machine has a power amplifier, which is in fact a boost converter. So the voltage goes up, and we limit the output voltage, which is also the bias voltage of the capacitor, up to 80 volts. So
okay. Do you have also in mind to ramp this voltage up to higher voltages?
Well, there is the idea, because we always get this question. So in future, we might change or make a new version of the MADCAP. But in fact, for what we see now is that it's not necessarily the bias voltage that has an influence on the power loss. It's the voltage ripple and the current ripple. So those two, you can achieve those also at a low bias voltage. Of course, if at a high bias voltage, the capacitance drops, this has an influence on the voltage ripple. And then, yeah, you can do these measurements and substitute your values for a lower capacitance. But
for example, in electrolytic capacitors, the ESR is strongly depending on the voltage level. For example, at low voltage capacitors, you use electrolytes which have a much higher conductivity and therefore lower ESR than in high voltage capacitors. And that would mean that if you compare a low voltage capacitor with a high voltage capacitor, from intrinsic properties, you will observe different ESR values. And then you could not, let's say, apply that view. So you have to, in fact, to compare really apples with apples. You really have to apply in high voltage and get also the high voltage feedback from your test. So this is crucial. So in that sense, I would recommend that you try to improve your test system also for higher voltages, because I think then in power electronics, the voltage levels will rise.
Yes. And indeed, if you want to go more into that market, it makes indeed sense to do so. The reason why it's now 80 volt is because we use state-of-the-art gallium nitride switches who are rated for 100 volt. And we use these because then we can achieve the very high steep current slopes. So it was a design choice from the beginning. Yeah, another comment on this electrolyte capacitors, where indeed you can have a change of ESR. What we know from our customers who use the machine is that they often have a family of capacitors, and then they test the lower voltage capacitors and see close to the max rating how the ESR changes or how the behavior is in general, and then use this knowledge to extrapolate it for their higher voltage electrolytes. So this is a solution for now, like a workaround, you could say. But indeed, it's true. It all depends on the application in the end. So yes, I hope this answers your question.
Yeah, okay. I have a different opinion here, but okay. Oh, good.
So yeah, so you would not use these electrolytes at
No,
the
the
lower
thing is
voltage.
that the electrolytes at high voltage systems are different. You could not use, let's say, the experiments at low voltage tests for high voltage systems. The electrolytes are different. That means you're talking about completely different systems. That means the electrolyte is a different composition. The oxide has a different quality in such high voltage systems. And then you could not compare then low voltage experiments at the higher voltage levels and compare them with low voltage capacitors, because the systems are different. And when you have different chemistries, for example, involved, then you could not use your measurement at high to let's say to scale it up to different higher voltage levels.
May I ask what voltages do you speak about when you say high voltage?
High 450 volts, 500 volts.
Ah, yeah, okay. Yeah, no, I had in mind like just above the limit, so 100 volt or 150 volt capacitor. So, okay, yeah, indeed, for if you go to, yeah, but that's a different range of, yeah, working range of capacitors.
Yeah, but I mean that it would be highly, because I think your idea is great, and you should look towards extending your voltage range. And also GAN will also be soon be operated at higher voltages when we talk about vertical structures, HEMS, etc. So there might be also a relevant interest in that.
Yes, it's for sure something we're taking to the future. We also did this, by the way, for our inductor measurement machine, because we brought out just a few months ago a high voltage version up to 1000 volts. So it's always a work in progress to make new and yeah, more advanced machines.
Gentlemen, our talk gets to an end. It was a very fruitful crosstalk. I really enjoyed it, and I'm looking forward to more of these events. Probably next year, I may plan a real event again. This year, Corona has blocked traveling for a lot of people in the world, and it had made no sense to look for a normal conference. So I can wish all the best and say Merry Christmas, Happy New Year, and have peace in the world. That's what we need. You see, I grew up in peace, and when I look around, it's crazy, but we all can only hope that this will end. And so I will say, have a nice evening, and see you at one of the upcoming events. If it's APEC, PCIM, EPE, or EPE is quite a couple of months away from us, but maybe one of these days, Thomas, I get up to Denmark, which is in a riding, in a
maybe
car
you can
ride.
You can, when you drive to Aalborg, you might, let's say,
yeah,
stop
Aalborg
in
is
Sunderborg.
next year.
So your
Yeah.
Aalborg is EP is in Aalborg next year, and of course maybe from when you travel from Kiel to Aalborg, you can stop in Sunderborg and visit my lab. Would be highly appreciated, Bodo.
Okay.
That you stop by.
I
Anyone could come. Also here, Ron. I know you're from time to time. You're also in Europe. I don't know, but if you are highly let's say invited to visit my lab and see what we are doing here. Maybe this is interesting for AVX as well. So
Yes, thank you. I hope we could. Yes.
Okay, gentlemen. Have a nice rest of the day.